Welcome to the Math Record. Today I'll be covering the last concept in my calculus class, Taylor and Maclaurin series. In our last video, we changed equations that look like geometric series into a power series. Well, what happens if those equations don't look like geometric series? Well, that's where we use the idea of Taylor and Maclaurin series. So a Taylor series has the formula, the summation from k equals 0 to infinity of, now we're going to use higher order derivatives, so a higher order derivative of degree k evaluated at x equals c divided by k factorial multiplied by x minus c to a power of k. And now for Maclaurin series. A Maclaurin series is exactly the same thing as a Taylor series, except now your c is replaced with 0. And the reason is because a Taylor series, we could center our equation at x equals c for any number, while for a Maclaurin series, we center at 0. And what this means is, let's say we have an equation f of x. If we want to center f of x at x equals 1, x equals 2, x equals 3, etc., or x equals like 1/2, or x equals pi, then we could use the Taylor series. But if we want to specifically center around x equals 0, then we use the Maclaurin series. But they both pretty much do the same thing. So let's try to understand this with an example. So let's say f of x equals sine of x. Oops, I didn't mean to leave that dot there. And we want to find the Taylor series up to degree 5. And we want to find this equation centered at, let's say, x equals pi over 2. So to do this, I usually like to make a table. And 3. Okay. And the first one I'm going to keep track is your degree. So I'm going to label this with k. The second one we're going to keep track of is our derivatives, our higher order derivatives. And the next one we're going to keep track is our higher order derivative evaluated at our point C, which is also where we're centering it, so pi over 2 in this case. And the last one is going to give us our terms. X minus c to the power of k. So as you see as we remember from our Taylor series, it had a summation. So whatever terms that came out here, we're going to add them together to get our Taylor series. So our degree, we're going up to 5, so 0, 1, 2, 3, 4, 5. So 0 is our original equation, so that's sine of x. Our first derivative is cosine of x. Our second derivative is derivative of cosine, which is negative sine. The third derivative is the derivative of negative sine, which is negative cosine. And the derivative of negative cosine is positive sine, because negative sine is positive sine. And the derivative of sine is cosine. And as you see in this table, it kind of makes it easy to keep track of your derivatives. Okay, now let's evaluate derivatives at our center. So sine of pi over 2 is 1. Cosine of pi over 2 is 0. Negative sine of pi over 2 is negative 1. Negative cosine of pi over 2 is 0. And sine of pi over 2 is 1. And cosine of pi over 2 is 0. Now following our formula, we could plug everything in. So this one's a 1 divided by 0 factorial. X minus our center, pi over 2, pi over 0. Now we have 0 divided by 1 as your k now, factorial. X minus pi over 2 to the power 1. Now we have negative 1 divided by 2 factorial, x minus pi over 2 to the power 2. Now we have 0 again, so 0 divided by 3 factorial, x minus pi over 2 divided by to the power of 3. Now we have 1 factorial divided by 4 factorial. 1 divided by 4 factorial, x minus pi over 2 to the power of 4. Now last one is 5, so 0 divided by 5 factorial, x minus pi over 2 to the power 5. And immediately we could just take out this one, and this one, because there's zeros for all of them, which makes sense because we just found it here. And if we have zeros in our derivative, when we multiply it to anything else, anything multiplied by 0 is 0. So those nothing. So we only had to add these three. So 1 divided by 0 factorial, that's 1. X minus power 2, which is 1. So 1 divided by 1 times 1 is 1. So sine of x, the first term is 1. The second one is minus 1 over 2 factorial, x minus power over 2 to power 2. You can simplify 1 over 2 factorial to 2, but I like to keep the factorial. This is going to look nicer later on. Now we have 1 over 4 factorial, and x minus power over 2 to power 4. And I said before, you can evaluate 1 over 4 factorial, so you can simplify it. So it's 4 times 3 times 2 times 1. But I usually like to keep it in the factorial, because looking at this, it looks way nicer. And you can kind of see the pattern if you want to add more higher order derivatives. Okay, so this is our Taylor series up to degree 5, centered at pi over 2. So even though it's up to degree 5, we have up to degree 4 here. So why is that? Well, remember in our chart, our sine of our fifth degree had a derivative at 0, centered at pi over 2. And that's the reason why. So our fourth degree is basically the same as our fifth degree Taylor polynomial. So why is a Taylor polynomial important or useful? Well, basically, let's say we want to find the value of sine of pi over 2 plus 1/2, but we don't know how sine works. Well, basically, instead of using this, we could use this formula. So plugging it in, we have 1 minus 1 over 2 factorial. X, which is pi over 2 plus 1/2, minus pi over 2 is 1/2 to power 2, plus 1 over 4 factorial. X, which is pi over 2 plus 1/2 minus pi over 2, that's 1/2 to the power 4. And if you use your calculator, we should get something about 0.877604. And the actual sine value, the sine of pi over 2 plus 1/2, that is equal to 0.877583. Comparing these two, that's actually a pretty close approximation, which is what the Taylor series is doing. If you want an even closer approximation, as usual with a series, you just add more terms. So add more terms. And you can just look at the pattern of this to add more if you want. But usually, if you want to get a really, really close approximation, we just add more terms. But once you reach like a decent amount, I think this is pretty close, then we could just stop. So that looks pretty nice. Okay, so I'm going to miniaturize this. And next thing we're going to cover, which is for Taylor polynomial, which is similar to alternating series, is that they have an error estimate. Except for a Taylor polynomial, they have something called a Lagrange error bound. But basically, they have the same idea as our error estimate for our alternating series. They say that the sum of the first n terms, the error of those sum is less than the n plus first term. So writing that for the Lagrange error bound, remember our formula was a derivative, a higher order derivative at c divided by k factorial times x minus c to the power k. So our n plus first term means we substitute our k with n plus 1. So in our case, our Lagrange error bound is going to be f of f of n plus 1, evaluated at some point, and divided by n plus 1 factorial times x minus, where we're going to center our equation, to the power of n plus 1. Okay, and the difference is that the Lagrange error bound actually is a little different for our higher order derivative. It's actually evaluated at point A and an absolute value. So what this actually means is that we're going to find the maximum value between some point x and where we're going to center our equation c. So let's use the Lagrange error bound to find the error of our approximate Taylor series versus compared to our actual. So our maximum value, so remember our derivative for our fifth degree, when we did in our chart, was cosine of x. So we want to find the fifth plus 1, which is the sixth higher order derivative. The derivative of cosine is negative sine. And then we take the magnitude of that. So the magnitude of negative sine of x. So what is that compared? So what's the maximum value of negative sine of x from x to c? Well, what's this x value? Well, we want to compare pi over 2 plus 1 half. So pi over 2 plus 1 half to our center of our equation, which is 2 pi over 2. Or you can switch the place. So pi over 2 to pi over 2 plus 1 half. So what's the maximum possible value? Well, if we think about it, the highest possible value for sine of x is at 1. And that's when it's is 1 is when it's at x is equal to pi over 2. So at x equals pi over 2, we get sine of 1. Negative 1, take the absolute value, is 1. And that's basically what it means. We're just looking for the maximum possible like disorder in our derivative. So from there we have 1. Our n in this case was 6. So it's 5 plus 1, which gets 6 factorial. Our x value, which we want to evaluate, is pi over 2 plus 1 half minus our center of our equation, which is pi over 2, to power n plus 1, which we set was 5 plus 1, which is 6. So using this and using our calculator, we should come out with an error that's about 0.000022, which pretty much matches with the error here. Because if you look at it, 0.8, so let's write that a little bigger, 0.877604 compared to 0.877583, that error from our actual answer is around 0.0022, 0.00022. And that's basically everything for this video. Thanks for watching, and that basically completes everything for our calculus class.